մի քիչ ուշ վերջացավ։ Ամեն դեպս շատ ուրախ եմ, որ դուք ստեղ եք, պետք է ունենանք նույն ձևի ֆորմատը, պետք է խոսամ անգլերեն, բայց դեռ հայկական, ես պետք է այսօր հայկական հայերենով կա բացատրություն մի քիչ, ուրեմն այսօր պետք է երկրորդ զեկուցում տամ, պետք է խոսանք Լուսնի մասին և Մարսի մասին։ Պետք է խոսանք այն ՆԱՍԱ-ի պրոջեկտները, որը տեղի ունենում, որտեղ մենք ապրում ենք շատ հետաքրքիր ժամանակի միջանցքներում, so very interesting time, extraordinary time. I would say that when the new era after Apollo mission, we're going to start, investigating the moon, so learning from what we learned from Apollo and going and building some new interesting structures and moving from the moon to Mars, and you're gonna witness it. So I'm going to talk about the major objectives of the mission, of missions, and what we can learn. So first I want to start with the our next door neighbor, the moon. So this is the moon, as you see, that's closest to us. Let's say 2006, at a distance of 4,000. Farther away from us. That's why that is smaller. At a distance of 405,978 kilometers away from Earth, and this one 357. And you can see that it's about 10% difference, and you can visibly see the difference, right? So that's the change in orbit between Earth and the Moon. And so you can see that the surface is very homogeneous, and we already been there. And the Moon doesn't have an atmosphere, and it doesn't have a magnetic field. It's open to the outer space. It's open to the solar wind. It's open to any kind of disturbances, to any kind of solar flares, solar wind, ground mass ejections, any disturbances that I discussed yesterday. So I'm going to show you a small movie that discusses. So today I'm going to show a few movies.
To every inch of spacecraft, the sun is a damaging source of radiation. All objects traveling through space must contend with this hazard, including planets. Even the moon has the scars to prove it. New NASA research suggests that some of the coloration we see on the moon could actually be a form of sunburn.
The leading hypothesis is that the magnetic fields are blocking some portion of the solar wind from reaching the surface.
The solar wind is the sun's continuous envelope of particles of radiation that fills the inner solar system. Earth's magnetic field provides a strong.
That's what I wanted to show this kind of animation, to show you that the solar wind always interacts with the surface of the moon, because moon doesn't have an atmosphere, and that creates very interesting effects that I can talk about later on today. Okay, so now we're ready for Artemis 1 program. This is the rocket that's on the launch pad. It was supposed to happen yesterday, and it didn't. Yesterday, Jarek Čistacvec, where ми унесли hurricane, Florida image. That created a lot of challenges. So that's why the launch will be moved probably in coming days, because it looks like it's just weather. Okay, because in Florida now we have hurricane season up to November, and so from time to time we have those hurricanes that coming from the Caribbean all the way through Florida. So yeah, that opens up the new era in exploration of the moon. So that's how it's going to work. The Artemis is going to start from here. Yeah, so launching from here and then going through the moon a couple of times around the moon and coming back. Okay, so it's just a technology demonstration to show that new rocket built by 2 American companies work very well, and will have a successful the orbits around the moon. So in 2 years later, into 2024, we're going to have the second, the Artemis 2, that will take 2 humans and fly around the moon. It will have basically the same orbit as I showed in the Artemis 1, but with people now. Okay, we'll go also twice and then come back. So that would be that technology demonstration with the human involved, with humans involved. So that will be NASA and Canadian Space Agency in 2024. It will be total 8-day mission. So after we successfully go through the second, we're gonna launch the third one, Artemis 3. So the Artemis 3 is the one that will go. This is the orbit. Will go. So we will have 2. We'll have the orbiter that will go around the moon, and we'll have also the launcher. So the lander. So we'll have a lander that will land on the moon with 2 astronauts, with 1 lady and one male and 1 female. Okay, and 1 male and 1 female will stay in orbit, and they will stay there for a full week, exploring the moon. Okay, and that would be the third phase, the beginning of the new era, when we're gonna make probably twice a year the launches and start building the base. So we are also going to show you this movie, the short movie about phase 3. That's animation of the Artemis 3. It's the first stage. Booster release.
Չինի մեծացնելն
Պետք է որ նորություն լինի, այո։ Բայց ես կարող եմ Եվ այս հիմա գնում է դեպի Լուսին և պետք է հանդիպի Էլոն Մասկի ռակետ և միանա, պետք է ռանդևու ունենա։
Սա ապագայում է հիմա In the past or in the future?
No, it's in the future, it's animation, yeah, it's animation, how it's going to work. Oh, that's already, okay, so that's the lander, goes down, that's the Elon Musk's lander. Plot jest ժամանակի совсем добра. So now I want to talk about the lessons learned, about the why we're going to go, why we need to go to the moon. So first, let's start with the Apollo mission. Apollo 11 to Apollo 16, we had 6 successful missions. You can see here, all the 11 the landing sites for each of the missions. And you can see it's mostly the equatorial region of the moon. Actually, the moon is a pretty small body. If you, just for comparison, if you imagine the distance between the New York City and Los Angeles, okay, so it normally takes about 5.5 hours to fly from New York City to Los Angeles. So the moon is 30% smaller than the distance between New York City and Los Angeles. So
make up better noise rather than go to all.
Yeah, no. And those regions, as you can see, they're mostly all covering the volcanically active regions in the past. So it's basalt mostly, which is black, okay, and they're young. So we now know about the lunar basalt pretty well because we brought so much material to over 19 laboratories over the planet. So, but now we're going to go to the South Pole. To the South Pole, the shot takirtere, where petke laf dramasin chikosam inchu masin inchu amar portef this missions found water during Lusni, and the water was deposited on the moon as comets hit the surface. And water can be produced through the chemical reactions triggered by the solar wind. The solar wind that I showed you from the beginning. So, and the water molecules then can migrate around the moon. And actually, that even there is the communication between the Earth
What
and...
M0 means? M0.
Pardon?
M0 on your second paragraph.
So found
Found M0 solid ice. But we
Found...
M0.
No, that's...
Maybe amount?
found no.
That's the... Well, not the solid. It's just M. It's the extra M.
Imagine.
Not solid, but whiskey frosting ice. Yeah, dispersed through the sample. And this impact of the lunar surface by micrometeorites can explain these unexpected findings. So I'm going to show you the movie. You can imagine that's the impact of the moon by the micrometeorites. That was observed by the previous missions. So now we're going to the lunar pole, which is the geologically old surface. When I say geologically old surface, I'm talking about 4.4 billion years old. Okay, it's basically pretty close to the times when the life started on Earth, at least the beginning of the secondary atmosphere. So therefore, if we study that region of the South Pole, then we can learn a lot about our young sun, and we can learn about the early solar system. And the reason why, because the South Pole is not subject to the weathering from the solar wind. Okay, so the sun barely grazes the horizon, and shadows, and it has those craters, heavily cratered areas, and the sun actually practically never enters this region. The shadows never fade. So it has this, the icicles and floors are in internal darkness. So, and ice is the source of water for the future missions. So that's why, from that point of view, it's a geologically old area. So we want to know what's the isotopic compositions, how it differs from the equatorial regions of the sun, of the moon, and also, whether we can use the water for the future lunar base.
Is there water, more precisely, ice as a source of water on the surface of the moon?
Yes. We have ice. That's right, and we have enough in order to supply it for the functionality of
But
astrophysics. Yeah. We already know that that's a Jerusalem, that we can drink. So, yeah. So basically, before I go any further, this is very important to NASA because the Chinese Space Agency already started to also explore the moon. They want to build the lunar base. It's another kind of a space race now between China and the United States. And you see that the Chang'e E4 lander and the U2 rover now are on the far side of the moon, on the one that you would never see unless you circle around the moon. And so this is the lander, and this is the rover that actually also found water on the far side of the moon. And also they have a small telescope. They're making observations. So this far side of the moon is a very interesting place because, for instance, you can build a radio observatory, an antenna that will shield the all radio signals from Earth because we have those human-made signals due to the radio communication. And if you want to measure extremely faint signals, for instance, we want to measure magnetic fields. Yesterday I talked about exoplanetary magnetic fields. As the particles gyrate around magnetic field lines, they generate radio emission. But this radio emission is no more pretty faint, and so the only way to measure is to build extremely sensitive radio telescope. So it should be in space, not only just in space, but in the far side of the moon, to block everything that we have from human activities. Okay, so now what the Artemis mission will explore. So first, as I said, that this is the heavily cratered area. It has permanently shadowed regions. So these regions that never saw any sunlight. Okay, so that's the temperature is extremely low. We're talking about temperatures minus -250 degrees Celsius. So the point is that the magnetic field was present on the moon 4.4 billion years ago, and now it deflected particles. So South Pole is an interesting place to expect the interaction of the energetic particles that are going to go along the magnetic field into the polar region. Every time we have a flare today, we normally see the particles penetrating in the polar regions of the south and north pole, creating northern light, right? So here we expect to find interesting products of the interaction of the energetic particles with the pole. So it will shed light on the history of the moon and its magnetic field, as I said, and it's also the reason to resume the robotic and human exploration of the lunar surface, to drill the surface, to understand the lunar geology. So I'm going to show you the movie. This is an example of the future NASA plans for the lunar base. So where we're going to have the first colony, and of course it's going to be built, under because we need a certain shielding from the ionizing radiation. So we're now thinking about where to build it. What is the appropriate landscape on the moon that can efficiently shield the astronauts from the ionizing radiation from the sun during flares. So that's the so-called lava tubes is one good example. So we see here it's like subsurface caves in the huge caves. I'm talking about like 100 kilometers wide. So that the result of this, the tunnels formed during the eruption of basaltic lava. So forming those kind of structures, it's like bridge-like structures that can cover, so astronauts can live inside of those caves, and they're pretty large, between 500 to 900 meters. So we already have those structures. we observe the structures, and potentially that would be the site for the first lunar base. By the way, so the same structures we see on Mars too, because that's a result of the enhanced volcanic activity. So if you have a lot of lava, sometimes then the lava, outside that goes out, cools down pretty quickly with respect to the lava down, and so it creates this kind of structure. So that would be the interesting place to. That's the. You can imagine this is the Philadelphia city with respect to the whole area created by lava. Okay, so the lava tube is one interesting opportunity for us to explore. So it contains chemicals like water, ice, and volatile chemicals that can be used to make fuel. So we can use the water, ice for the human consumption, and also the chemicals to make fuel. It also, as I said, shields humans from solar radiation, and it provides the easy access to surface. So all those factors make lava tubes as a very attractive, structures to for the lunar base. Okay, the moon, the why to have the moon base? Again, it's a middle point for flights to Mars, because in any case we have to create settlements on Mars, and the best way to do it to first to have the base on the moon as the middle point between the Earth and Mars. Okay, so as I said, then to study the young sun and the solar system, the important point to build space observatories. So the moon provides a very interesting opportunity to build huge telescopes, because the surface gravity is 6 times. If you want to try to walk on the moon, you're going to jump on the moon, because your weight will be 6 times less than here. Okay, so for instance, if you weigh like 60 kilograms, you will weigh there like a baby, 10 kilograms only. So it's probably a nice feeling to feel like 10 kilograms, right? And but that will ease. Պետք է շատ հեշտությամբ օգտագործել դա սարքելու աստղայտարան սարքելու, մեծ աստղայտարան, մեծ հեռադիտակը, որովհետև օրինակ տեսնում եք այստեղ, այս տեսակի կրեկերները can be used to build a mirror, the big mirrors. And now at NASA Goddard, we have an effort.
You mean for optics?
Yeah. So at NASA Goddard, we have an effort over the last 10 years, when people already used the, because we know that lunar dust, so we use the lunar dust to bake it, and they use the rotator, fast rotator, in order to create a paraboloid. Right, like on the moon, to do it in a faster way, very thin paraboloid, and put that on the moon to create a space telescope, right? So, because you have no weather there, no atmosphere, it's much better than a space telescope. And you can build 100-meter telescope. That means that you have unlimited access to space. You can basically, open completely new universe for you. Now that the Hubble Space Telescope is 2.4 meters, okay, it's like close to the size of the Huracán 2.6-meter telescope. And with 2.4-meter telescope, we uncover the whole new universe. We're now rewriting the textbooks, okay, with this revolutionary discovery of Hubble. And now we have another one, James Webb Space Telescope, that we discussed yesterday. That's 6.5-meter telescope, okay, about 2.5 times bigger. But I mean, with the sensors, it makes it 100 times more powerful, okay, in terms of information sensitivity. With this one, you will have not just 100 times, but tens of thousands times bigger, because if you build not 6.5-meter, but the 50 to 100-meter telescope, just to use the crater, that will create a new lunar space telescope. And now, I'm not talking about just just dreams, but I'm talking about real projects. So now we have real projects started about 6-7 years ago, and got to the point of detailed calculations, how from the beginning to the pretty much technical maturity level. We call it technical maturity level 6, which is pretty good. 10 is the max. Yeah, so this is very interesting opportunity. And when I talked about this mission in Japan just about 3 months ago, Japanese was also interested that to join the project with NASA and basically to build those observatories. Okay, so the lunar, another project, it's called Lunar Crater Radio Telescope. So another thing, it's much easier to build, right? You don't need much of the sensitivity. It's a radio telescope. It's so you can build a radio telescope exactly in the way like we have the Hayrapetian, the radio telescope, but on the moon. Will be much easier to build. You don't need that. You don't need this very precise optics for that. For instance, if your telescope is like works in the millimeter wavelengths. So, but you will open the new universe. For the radio telescopes, it's really a new universe because the ionosphere, the upper layer of our Earth, Медновати very masna shot take if is the radiation chance in nature get deflected, and so that's why you need to use a telescope, the telescope outside the Earth. So I'm talking about frequencies below 10 megahertz, something 10 megahertz. So we don't know anything about our universe below like 1 megahertz. We don't have that information. We want to know with magnetic fields in our galaxy, it will open completely new structures. Yeah, so I'm really excited about it because we know what to expect. We know that a lot of shock waves going on, a lot of free electrons, a lot of magnetic field, free magnetic field, but we don't have the mapping, the magnetic map of our galaxy, for instance. We know some very, have a rough picture, but with this telescope, we will for the first time have a relatively inexpensive, pretty cheap, I would say, way to study the universe at low frequency universe around us. Okay, so. Yeah, and so the far side, as I say, that the low frequency, and because, again, I just want to repeat, because, that the far side of the moon is shielded from the radio noise created by the human activity, okay, that we use every day, television, radio, and so on, this communication. And also, we're going to drill from tens to centimeters to meters to 100 meters depth to study lunar geology, to know the history of the moon. And so this is I'll show you the movie about constructing the lunar safe haven. It's one of the projects that's a funded project, this mission. so in the interest of time, so I'm not going to show the full movie, but it tells you that how detailed the investigations, the technical details are now with NASA spending money on that. So we're looking at every aspect of the technical aspect of the excavation of Mars, and the next one is, I think it's the drilling. Yeah, drilling on the moon. So that's another movie of the driller that will go all the way to 100 meters. So it will start from meters and will go down, and it will create a good opportunity.
How deep?
200 meters. But then we will use this to drill the Martian surface. So the lunar project will be just an introduction to Martian project, because it's closer to us, and also because Southern Pole has a lot of ice, it will be easier to drill. Okay, so so basically one question that we want to answer is, if you look at what Apollo mission found, they looked at the composition, chemical composition, and you can look here. The white circles are chemical composition of the regolith from the moon, white one, and the black one is Earth. So you can compare in abundance. Okay, so it's a sodium, magnesium, aluminum, silicon, potassium, calcium, different chemical elements. So what you can see here, so that the sodium and potassium are very different. So and so this one, see that how big the difference is, and here those two. So we want to understand why. For instance, the moon has the deficit of sodium and deficit of potassium. So that was discovered by Apollo 16 lunar sample brought to Earth. So, and in our recent paper, we suggested an explanation for that. Basically, the point is that this is the result of the interaction of those giant clouds emanating from the sun to the solar flares. Interacting with the lunar soil, and that way extracting, because it's pretty easy to extract sodium and potassium, as the models show. And so depending on how frequently those flares occur, we developed a model to answer the question whether the sun was the fast rotator or the slow rotator. There's two scenarios how the sun can go when it was very young, okay, after T20 phase. And so basically, that was saturation, that it can go that way, when that's X-ray radiation from the sun, or that way. This is the slow rotator, this is the fast rotator, and you can see the X-ray luminosity can vary more than order of magnitude, more than 10 times. So now we want to understand, what scenario, what was our sun? Was it slow rotator or fast rotator? So, and this is the model for our sun that we developed. Okay, so this is the, at one point, this is the magnetic skeleton. If you take the X-ray of the sun, when it was young, I'm talking about, that's what you will see. It was rotating 3 times faster than it is today. And imagine that was one magnetic skeleton, if you take the X-ray of the sun. And then, like 6 months later, that's what you're going to see. A few months later, you're going to see something like that. So the magnetic field is highly disorganized. So those magnetic structures will create conditions for much more frequent flares that will interact with the lunar surface and extract those sodium and potassium. So using those models, we found that the CMEs were pretty less frequent than you would expect from the fast rotator, and is basically consistent with the measurements from Apollo missions of sodium and potassium. So another question is those particles. So yesterday I talked about it, that those giant ejections, they create the X-ray particles. And X-ray particles, they penetrate into the surface of the moon, and they are recorders of the different isotopes, of chemical isotopes. So forming boron, nitrogen, azote, nitrogen 14, nitrogen 15, and iron 60. Now iron 60, this is the isotope of iron, which can only be created during supernova explosion. So we recently found iron 60 on the bottom of the ocean. That means that the dust enriched with iron 60 was swept from the supernova and was absorbed by the Earth. So it was found not only on Earth, but it was found on the Moon too. Okay, which also tells us that we can see echoes of supernova explosions, which actually happened only about 2 million years ago, because iron 60 decays with around that time. So and we see the pretty large amount that suggests that that was pretty recent event, and might be that created the bubble that we live in. So we live in a bubble, so the region of the relatively low density. I mean, we're talking about a few tenths of parsecs, or a few tenths of light years, the distance, of this kind of cavity that was created by the explosion. So that would be a very interesting question also to look at from the South Pole. So, and now I'm going to talk a little bit about Mars. Okay, so next point will be to move to Mars and to use the technologies and the lessons learned from the Moon to explore Mars. And you've probably seen the movie The Martian. Have you seen the movie? The select movie? The movie was actually consulted with my colleague Jim Green, who participated in the conference, the German conference last year. So now we're working together with Jim Green to develop scenarios to terraform Mars. Because if we're going to move there, we need to create some kind of temperate climate that is kind of like a little bit more friendlier than it's today. Because if the Moon has no atmosphere at all, Mars does have an atmosphere. It does have an atmosphere which is 160 times thinner than the Earth's atmosphere. It's an atmosphere that you cannot breathe in. Of course, you need a spacesuit. But we're asking the question whether we can do anything to increase its mass of the atmosphere to the level when the liquid water can exist, on a permanent base. Because now, if you put water, it will immediately evaporate. Okay, there is no standing bodies of the liquid water. So therefore, when I say terraforming means that forming the conditions like on Earth. Terra that means Earth. Okay. So, how to terraform Mars? So we need the following steps to do. First, we need to reduce the atmospheric escape. Mars doesn't have magnetic field. So it did have magnetic field, it lost its magnetic field. It's a smaller planet. It's 10 times lighter, less in mass than Earth. So its core got solidified much faster, and the magnetic field is formed due to the magnetic dynamo. You know this, you probably have seen those flashlights, the dynamo flashlight, right? So when you have when you have a molten core, and Mars did have a molten core, and it rotates, and it generates electric current, and electric current can produce magnetic field. Okay, and imagine this molten core got solidified, so now it's not molten anymore. So no matter how fast it rotates, there is no generation of electric currents. So the magnetic field. So now we have just a small residual magnetic field, like small ions of magnetic field. So therefore, to do that, the atmosphere escaped from the planet, and now that's why it's 160 times thinner. So what we need to do, we need to create some kind of magnetic field. So we propose artificial magnetic field. We'll talk about this. So therefore we need the ways to create a magnetic field. then we need to somehow respond to the Martian climate. We need to see that what kind of greenhouse gases we can introduce. On Earth, we're trying to fight global warming. On Mars, we want to create global warming. Okay, because if we can create a global warming, then we can start melting the ice on the poles, because Mars has those polar caps. And the polar caps, that I showed that in the first, let me go back to the first image, so that you can see, because unfortunately I don't have that. Oh yeah, that one. So you see here, so this is the frozen ice, sarutse, your frozen carbon dioxide. Okay, so it's frozen, but it's a lot of mass. So if you increase the temperature, you start to melt it. You start creating the from solid state a gas state, and it will build up and will work as a greenhouse gas. Because carbon dioxide is a powerful greenhouse gas, not only the carbon dioxide, but also water vapor. Water vapor, that's another greenhouse gas. So both of them can create very interesting conditions for them, for those artificial global warming. Yes, so, and so we need to respond to the Martian climate to make it more friendlier to humans who want to live there, and those are also ionizing radiation. And of course, if you have a thinner atmosphere, so therefore, the radiation from space, the particles, galactic cosmic rays, and the particles from the sun can easily penetrate in and can damage our skin, can damage our bodies, so therefore that's another thing. So you don't want to live, under the lava tubes that I showed all your life. You want to go out and walk a little bit, right? So we need to think about that too. So that's basically the major steps to terraform Mars. When people say terraforming Mars, that's what basically we mean. Okay, so. So basically, talking about another question to study on Mars is to find the life. So we believe that life was present on Mars because Mars had, and yesterday I didn't talk about it because I deliberately decided to leave it to today's lecture. So the point is that if life started on Earth, that means that we had right chemistry, we had water. Remember we talked about we had chemistry, and we need water, right, for that. So and the energy from the sun. So we had the same sun. Mars is just about 50% farther away than Earth, not that far. And it has the same kind of chemistry. It's even better because it has more boron, and the boron is this chemical element which is very beneficial for formation of the sugar called ribose. And so that's another good thing. Water, we see a lot of signatures of water. We see those dry river beds, and we see the bottoms of lakes. We see the dried lakes, a lot of them. So the recent rovers that we have, the Spirit, Opportunity, Perseverance, those 3 missions, the 3 rovers that now working on Mars, okay, on different regions. They in the equatorial part of the Mars. The Perseverance mission has this onboard chemical laboratory. It basically drills a little bit. And has a small laser, evaporates a little bit from the rock, and then grabs the material and puts into the chemical laboratory. It's that big. And then it hits it to temperature 800 degrees Celsius. And then it has a centrifuge. And it can decompose and study the chemistry of those rocks, okay? And it is looking for the molecules of life. So far, of course, we didn't find any on the surface, but what can be done later on, of course, I told you that because even if we had any any life, that the radiation from the sun, at the atmosphere of 160 times thinner than on Earth, this ionizing radiation will kill those molecules. But what will happen if the microbes, if the bacteria are still present? There is a good chance that can be found in the subsurface areas. Okay, at least the calculations show that we know the radiation environment on Mars. At least we need to drill 2 meters. So if we drill about 2 meters to 3 meters, then we can find the microbes. The reason why we have a good reason to believe that microbes can really still be operating on Mars, because a number of times we detected, and recently too, detected methane on Mars. Just simply from some certain caves, we found some methane coming out, and later on you don't see it because it has evaporated. So the methane can only be formed as a result of biological activity and the volcanic activity. Because the volcanic activity is not present anymore, and you only get very, very tiny portions from volcanic activity. The methane is a result of the decay of different biological processes, decay of microbes. So that's this scheme shows that how the methane can escape through cave regions, and then interact with the cosmic dust, and we can see not only methane but also its derivative products. So that's interesting interesting opportunity to look for methane. Methane, remember yesterday I was talking about it's a biosignature gas, but it's also a biosignature gas on Mars. Okay, so and again 3 times methane was detected sporadically. So NASA's Mars colonization outline. So we're talking about 2030s. So about 2033. We're probably going to start creating those, Mars cities. So now Elon Musk is very optimistic about it. So he puts a lot of money into it. So if we are successful with Artemis missions, then the next step by the end of 20s, might be in 6 years, we're going to be ready to have the Martian missions. And so in, I believe, like 2035, but they said 2033, I believe at 2035 to 2036, if the funds will be available at the level that we have today, then we will have the so-called Mars City. They have the Mars City, the name for it. That will be the first settlement to basically study and to live in a very strange environment. And of course, if we find life on Mars, that will be revolutionary. I would imagine that probably the first discovery of life on another planet will be discovery of life on Mars. Because on other exoplanets, the signal is too weak. So we need much bigger telescope. A telescope that will be probably built on the moon in order to see the signal that is required to decode information about life. So this is basically the phases of exploration of Mars, from basically getting there to starting to explore the area and building the ecosystems. And believe it or not, we have the research teams at major universities like the Massachusetts Institute of Technology, MIT. They are working on those lunar projects, including Stanford University. They have those teams that are developing different stages, how to grow food, let's say. That's one thing. How to grow food. Is the soil has enough nutrients? Nutrients in order to, if you put a plant, would it grow? So the question is yes, it will grow. So Mars has enough nutrients to support the growing of plants. And that's important, right? If you want to live there, you want to grow food that you will eat later on. So you have water, you have food, you have fuel, that's all you need. Then you have energy, you have the solar batteries, so you can create heat and electricity out of it. So that's so basically speaking, what we want to have currently you have this cold and dry planet, so the pressure is only 6 to 8 millipascals. This is about 160 times smaller than we observe on Earth. So therefore, we want to increase the temperature. We want to increase the temperature and we want to increase the pressure. So what do we have now when we look at the atmosphere? It's a 95.9%, roughly 96% of carbon dioxide. Okay, so it has a little bit argon, 2% of azote, the nitrogen, a little bit of O2, and carbon monoxide. So it's mostly carbon dioxide. So, and carbon dioxide is the greenhouse gas. So therefore, if we can increase it from the, as I said, from polar caps, we can increase the temperature. Okay. So and nitrogen again escaped. So it had the same kind of nitrogen atmosphere that we have today. We have today here on Earth, but because, as I said, Mars lost magnetic field, it lost also an atmosphere. So that's another the case study to understand how planets lose atmospheres. Because through Mars, compared Mars and Venus and Earth, we have 3 exoplanets. We can develop models how they respond to the radiation from ionizing radiation from the sun, how they lose atmospheres. I mean, what kind of rain they have, and then apply to understand other exoplanets. So this is the different, the topography. So you can see those, the regions of the redder regions above us, the background, and these blue regions are kind of like, beneath the, like the sea, dry sea. So this is the topography of the moon. So we have this is very well defined map because we had so many missions to Mars, so we know Mars pretty well. And you know what? We probably know Mars better than we know Earth, because the Earth, 2/3 of the surface of Earth is covered by oceans, very deep oceans, and we don't know our oceans very well, right? So, but we know Mars well, and we know the Moon much better than our planet, yeah, because it doesn't have any water anymore. So temperature. So this is the temperature variation. So we're talking about that's temperature in Celsius. Okay, so don't look at Fahrenheit. Fahrenheit is temperature used in the United States. But you can see the variation of the temperature depending on the part of the day from minus 90 degrees Celsius. Minus 90 degrees Celsius goes all the way to 0. Okay, it's pretty good, right? So, and then back that night to let's say minus 90. So it's a huge variation of temperature from minus 90 degrees Celsius to 0. Well, and why? Because it doesn't have atmosphere, and the second reason, it doesn't have oceans, because ocean is a very good thermal regulator of climate. So because of thermal capacity of oceans, water is a good supporter of life, not as a good solvent, but also a good regulator of the temperature variations. So your temperature variations on Earth are very small, like that 40 degrees, not 90 degrees. So that, okay, so that's another reason to reduce this temperature variation. So, so we know that, as I said, the early Mars was a hospital place. It has the pressure at least half a bar, or half of the pressure that we see here on Earth. It had a magnetic field, it had a magnetosphere. It had oceans covering about 30% of the northern hemisphere, and we know that from the residuals, how much we have today before escape, and it had a nitrogen-rich atmosphere. So basically, all the ingredients that we need to create life, it did have before. So that's why we believe that there's a good reason to that was the planet. The planet was covered with oceans. This was a good planet just about 4 billion years ago, and that was happened. Okay, so you will expect the same for Earth. So the future humans, like 1 billion years from now, they will find they will say that was today, that will be tomorrow, on Earth. Because the sun will be 10% brighter, so the 10% radiation sent to Earth will eventually boil the oceans and will evaporate all the water, and then eventually will, and extract all the carbon dioxide from the water, not only water vapor, and then increase the carbon dioxide pressure, and then will create also carbon dioxide-rich atmosphere, exactly like Mars. Okay.
Not very soon.
Not very soon, but still, this is important not only for us. It's important what kind of conditions we should look for on exoplanets. So the carbon dioxide will be probably, because most of those exoplanets that we look at are pretty old. They're like 7 billion years old, 6 billion years old, some of them are 10 billion years old. So that means that they're already kind of like a dead planets, okay, for their young stars. So therefore, that's the important for the assessment of, what to expect and where to find. So we need to look for, as I said yesterday, for the younger planets around younger stars that have a better chance to have more this kind of atmosphere, like young Mars. Okay. Young Mars is a good preview of a planet with the good habitable conditions. Okay, so now I already talked about it, that we need to reduce the level of ionized radiation to create more like Earth in order to grow crops. So therefore, we need to thicken the atmosphere for landing missions. So how to raise the pressure? That's one of the last points. We need to. So basically, at current conditions, we need to raise the pressure because this ionizing particles go down, and so this is the attitude, and that's the height that particles can reach in different atmospheres. The ground for 0.1 and the ionizing conditions. So and this is the total dosage in gray for different atmospheres. Show that we need to go to the level of at least 0.1 atmospheres to increase it at least 10 times to have something that can be reasonably well. So this is also the point, the triple point of water. Which the water can exist in the liquid state. So we need to go for the pressure, above this point, 0.06 in bars, so somewhere here. So that means that if we're 10 times thicker, have a 10 times thicker atmosphere, then we can have stable liquid water on the surface, and that's exactly what we need. Okay, so those calculations show what's the minimum conditions we need in order to have sustainable conditions for life. So, as I said before, we need to reduce erosion due to the solar wind, okay? In the planet that doesn't have a magnetic field. Currently, Mars is constantly losing this atmosphere. It's losing this atmosphere at the level of about 200 grams per second, okay, with normal conditions, but during flares, it can lose few kilograms per second. So it has as I said, very thin atmosphere and still losing it. So that's the loss of particles. This is the wind, solar wind, and that's the loss of particles. This is the information models. So it has, due to the photochemical escape of the oxygen, interacts with electrons, creates two hot oxygen atoms that escape because they have very high energy, escape with the energy greater than escape velocity. So therefore, we definitely need a magnetic field. So this is the artificial magnetic field that we will need, So we need to create a magnetic field at a certain distance that will, this is the one that is Mars, that can withstand the pressure from the solar wind. Okay, so from that point of view, the atmosphere of Mars will be safe. So that's we just this year published a paper that how to create this artificial magnetosphere. So the way to do it So, you know, from physics, you know that the magnetic field is created by electric current. So if you have electric current, current creates magnetic field. So therefore, the way that we think about it, we need to create artificial electric current. So now the question, how to create electric current? So this would be the atmosphere, you know, without the artificial magnetosphere, and this is with magnetosphere. So the point is that, you know, we need to either create some, you know, the magnetosphere far away, or that was one scenario far away from Mars, or we can use Phobos or Deimos, two satellites of. Skip this. This is a little bit more. A lot of physics there. Yeah. So what we want to do, if we can create, you know, the electric currents flowing around the planet. Okay, so that would behave, or put some kind of bar magnet. But you cannot put a bar magnet like in Mars. So there's some suggestions of if you put like millions of atomic bombs, you know, exploding in the center, you can create the molten core, and that will create the dynamo again, and then create the magnetic field. But that's very expensive project, and so it's just science fiction, so it's not going to work. So in that paper we explore this scenario to show that it doesn't work. But what can work is this, you know, I think this one. Yeah, so if this is Phobos, the Phobos is the closest moon of Mars, okay? And so it was distance of 6,000 kilometers. So if you can send the beam of electrons, you know, and put a few stations around, and so you can use the material of all Phobos to create those, to accelerate particles, and then send them, create the current, electric current around the orbit will create this magnetic field. So this magnetic field, we found that will be strong enough to shield the planet from the solar wind. So another thing is taking the atmosphere. So we need, as I said, just a small increase in temperature will release trapped carbon dioxide from the caps, from the polar caps, release water, and then if we also add methane. So the one suggestion is methanogens. I probably talked about it yesterday too. Those bacteria, methanogens that we have on Earth, they can grow on Mars. So you can put them on, they will absorb carbon dioxide, which is a lot on Mars, and